Okay, let's do this one. Do a trig one. So here's our function. We want to find all the open intervals on which the function is increasing or decreasing, and we're going to find all relative extrema. Okay, and they come together. Finding one really means you're getting the other also. They come in a kind of a package deal. Okay. So what do we probably have to do? We've got this domain. We're going to keep that in mind. We're only going to take one lap on the unit circle. But what do we have to do to find our critical numbers first? Differentiate. Okay. So now we got to be careful with that one. It's actually not a product rule. What? So. Okay, did everybody see that? Because when we write something using that notation, in fact, I am going to rewrite this. You don't have to. I mean, if you're okay not rewriting it, that's fine. But I'm going to, just so we can really remember what that means. If I do sine squared of x, remember that really means sine of x quantity squared, right? That's our shorthand, okay? So, I got chain rule issue here, right? I've got derivative of hand squared is 2 hand times the derivative of sine x is, okay? And then derivative of sine x is, okay, so there's our derivative, okay? This is yet another example of we're going to end up with trig equations, aren't we? Now, is this going to be undefined anymore? No, it's not. And how come? What's your rationale for that?
No dividing by zeros, no square root of values.
Okay, yeah, there's obviously no square roots of anything, but there's no division by zero. What kind of, I mean, what if I had slightly different, give me an example of a trig derivative, what might be included in that would cause me to have some asymptotes, and therefore some places where it's undefined. Like a tangent, or a cotangent, or a secant, or a cosecant, right? Any of those other trig functions are always going to have sines and or cosines on the bottom, right? And so those are, any trig function that comes with built-in asymptotes, places where the trig function is undefined, means those are going to be some places where the derivative is undefined, right? But because our derivative only involves products of sines and cosines, we're fine. Sines and cosines are no problem, right? They don't have any asymptotes in those trig functions, okay? So we can just inspect that and we can say it's everywhere defined, it's nowhere undefined, okay? But there are going to be potentially some places where the derivative equals 0, right? So we got to figure out where those are going to be. All right, so if we set this equal to 0, here's another one of those trig equations. And I've thrown quite a few of these at you recently. Yeah, once again, it's been a while since we've even been here, but I want you to be familiar with how to deal with these trig equations. This is something in my experience that hangs students up a lot, is solving trig equations. So what's our thinking on this? How are we going to deal with solving this trig equation? Okay, but instead of dividing by cosine x, what we really mean is we're going to factor out a cosine x, right? This looks, at first glance, does everybody see that this looks like it could be a little bit ugly because I've got both sines and cosines in this thing. But whenever we're solving any kind of an equation, and we could go back to quadratic equations as a model if we want to, our goal is always to write the function in factored form, right? If I can write it in factored form, then I can apply the zero product property. And in this case, when I factor out a cosine x, what's left behind?
2 sine x plus 1.
Okay, that's good, right? Because now my two factors, one of the factors has a cosine x in there, and that's fine. And the other one has only a sine x in it. So that actually makes life pretty good, right? By the zero product property, I know that the zeros of the function are going to be at the zeros of the factors when the factors are equal to 0, right? So we get one equation. You know, when we set this factor equal to 0, we get cosine x equals 0. Okay, so there's one solution. Now, we're looking on the domain x is between 0 and 2 pi. So we've just got to go to the unit circle and ask ourselves, where does that happen? Right? Where is that? What are the solutions of that trig equation on this domain, okay? Well, let's go ahead and find those. So cosine is the x or y coordinate. X. Okay, so where is x equal to 0?
Pi halves and 3 pi halves.
Okay, so it'd be at that point and that point, right? So if we're only taking one lap, we're going from 0 around to 2 pi, it's going to be there and there, right? So this would happen when x equals pi halves or x equals 3 halves pi. So those are two critical numbers, right? Now what about this other factor though? We gotta solve that one. When is this factor equal to 0?
When sin x equals 1 half.
Right, so 2 sine x plus 1 equals 0. Subtract 1 and divide by 2 when sine x equals minus 1 half. Okay, so that's the y coordinate, right? Sine is the y coordinate on the unit circle from last year, right? And so we want to find where are the places where the y coordinate is equal to negative 1 half. So that's going to be that point and that point, right? What were those? Remember?
7 pi over 6.
Yeah, always think about it in terms of the first quadrant, right? In the first quadrant, we've got these 3 special points that we always refer to. So this is the one that's going to have this is the one that's going to have coordinates.
Square root of 3 over 2 is 1 half.
This is the one that's going to be root 2 over 2, root 2 over 2, and this is the one that's 1 half square root of 3 over 2. So this is the one we want, isn't it? This is the one that's going to have a y coordinate of 1 half in quadrant 1, and that's the one that corresponds to an angle of pi 6 radians, right? So all we're going to do is we're just going to go pi halves plus an additional pi 6, or we're going to do 2 pi minus pi 6, right? So we end up at either 7/6 pi or 11/6 pi, right, would be the two angles where that's true, right, in the unit circle. So we end up with those, well, I guess 4 critical numbers, right? And then all we have to do is go to our table, and we're just going to try to figure out what's happening. Are those points of transition for the derivative or not, right? Okay, so that's the next step. Let's make a table. I'll call this f of x. Okay, so we've got f. F prime. And our domain was from 0 to 2 pi. And our critical numbers in order, the smallest one would have been pi halves. Okay, so that's going to be about there. Doesn't have to be exact. Oops. And then we had a little bit more than halfway there, a little bit past pi, so we would have had 7/6 pi. And then we would have had 3 halves pi. And then finally, clear up here, we've got 11/6 pi, right? Okay, what's going on at those places? What do I need to put in my f prime row? Zeros, right? Those were all places where the derivative was equal to 0. So we recognize those are all critical numbers. Okay? First derivative test. All the first derivative test is just seeing are those or are those not points of transition. So I'm asking you, how could we determine if this critical number is a point of transition of the first derivative? What do you think?
Take the approaching both sides.
We don't need to do that. It's too, I mean, it would work, but it's way too hard. Where are the only places where the derivative could possibly be 0 on our interval from 0 to 2 pi?
Plug in a random plane between those.
Okay, there's only 4 places, that's it. There can be no more. There can only be 4 places where the derivative has values of 0, right? Are there any places where the derivative is discontinuous? No, there aren't, because if there were, those would have been places where those would have shown up as undefined derivatives, right? So that tells us that every value of the derivative surrounding these and between these is just going to be normal values of the derivative, right? Where could we possibly transition from positive to negative or vice versa? Only at the zeros. Isn't that what zero means? Think about zero on a number line, right? If we just, if we take the real line, zero is the transition from the negatives to the positives, right? Okay, so that's the only place, the only possible places where we could be transitioning sign would be at those critical numbers. And so all we do is we just choose convenient test points around those critical numbers, and we'll make them as easy as we can. And we just want to know what are the signs of the derivatives. We don't even care about the values. We're just going to put, like we're going to pick a convenient point between 0 and pi halves. What might that be? Between 0 and pi halves. Like pi fourths. Pi fourths would be a good one, right? So we'll pick pi fourths. Okay? So if we pick pi fourths as a test point, all we've got to do is go up here to our derivative and check it out. Okay, so we're going to evaluate the derivative at pi fourths, but we can even be smart about that. I mean, I could plug it in right here, okay? But it'd be easier to do it in its factored form, right? Because we know that think about how when we're multiplying factors, what's the only way we could get a negative result? From thinking about the signs of the factors. I've got two factors I'm multiplying together. One's positive and one's negative, right? If they're both negative or both positive, the outcome is always going to be positive, right? So really, the form of the derivative that we want to use, oh, it's not that one, is the row below that. It's right here. Right, it's in factored form. So all I've got to do is just evaluate this factor, and I don't even care what the values are. I just want the signs, right? So we can abbreviate that in a little table. We can say that f prime of pi halves equals, is cosine of pi fourths, it should be, shouldn't it? Start over. That's our test point, right? So f prime of pi fourths. Is the cosine of pi fourths positive or negative? Positive. Yeah, it's in quadrant 1, isn't it? Right? So that's positive. The sine of pi fourths is what? Positive square root of 2 over 2 or something, right? Don't even really care though, because I get 2 times some number plus 1. What's the sign of that factor going to be? Positive. So the point is, positive times positive is positive. All I need to know is that that's a positive derivative there, right? So now where's the next test point that we probably want to choose? Where's it going to be? Between pi over 2 and 7/6 pi. So what would be a pretty easy one there? Pi. Yeah, let's pick pi. Right, so if we pick pi, we're going to go up here and evaluate that. What is f prime of pi? Cosine of pi is -1, right? And I don't even care that it's -1. All I care is that it's negative, right? What is the sign of pi? 0. So 2 times 0 plus 1 is positive. Negative times positive is negative. So what is this for sure? This is the first derivative test. By the first derivative test, if it's a critical number and it's a transition point of the derivative from positive to negative, it's a peak, right? And I would encourage you, I mean, this table is so cool because look, we can even determine, we know it's a 0 derivative, right? So we know that's going to be a horizontal tangent kind of derivative. It's not a sharp corner, right? So when we summarize this, we've got a horizontal tangent, and we're going from increasing to decreasing, and so there's our picture. It's a peak. It's a smooth peak. That's pretty cool, right? We know what that is. We've already got one of the test points because we can reuse this test point. It's already the left test point for our next critical number, So we got to pick a value between 7/6 pi and 3/2 pi. So what, like, how about 5/4? Right? That'd be on our unit circle, that would be the one right there. That'd be a convenient one to use, right? And you don't have to. You could pick a different one. So at 5/4 pi, what are we going to get? F prime of 5/4 pi is what? So what's the cosine of 5/4? Positive or negative? That's going to be the x-coordinate, right? So the x-coordinate of that point right there is negative. Okay, so we got negative. And then the sine of 5/4 pi. Now this one we're actually going to have to be a little bit careful with, aren't we? Right? So the sine of 5/4 pi, that's going to be negative square root of 2 over 2, right? So negative square root of 2 over 2 times 2 is just negative square root of 2. Negative square root of 2 plus 1, positive or negative? It's negative. So that's like 1.414, blah, 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 right? It's a little bit, but clearly the square root of 2 is bigger than 1, isn't it, right? So we get a negative number bigger than 1 plus 1 gives us negative times negative, positive, right? So we get, if that's positive, then we know we get a zero derivative, so we get a horizontal tangent. And we're going from decreasing, so walking downhill to walking uphill, so we get a smooth valley, get a smooth minimum. Okay? Convenient test point between 3/2 pi and 11/6 pi, 7/4. 7/4 would be like right there, right? So we're between those two. So what's that going to give us? Seven-fourths, cosine is going to be positive, right? And we're going to get the same answer here that we got for 5/4, aren't we? Right? The y coordinate is the same at 7/4 and 5/4. Both of those are going to have y coordinates of negative square root of 2 over 2. So we're going to get, once again, we're going to get our 2 times negative square root of 2 over 2 is negative square root of 2 plus 1 negative, just like it was in the last example. So that makes that negative. Once again, we're going to get increasing to decreasing, right? And then finally, we got to pick, this is an inconvenient one. We got to pick one, between here, right? So what do? Here's what I would do in this case. I would say, let's just think about this in terms of taking a limit, right? Because we can't really technically use 2 pi because it's not in our domain. But we could get as close to 2 pi as we want to, right? So if we were going to take a limit of this derivative as x approached 2 pi, and I do this by just writing the word limit up above this, right? What's that going to give us? Where am I going to put that? Gosh, I'm running out of room here. Down here, I guess. So we're taking a limit of the derivative as x approaches 2 pi. Well, we're really just doing the same thing. We're going to be able to evaluate that limit directly by plugging in 2 pi. So what is the cosine of 2 pi? 1. Good. Have you shown me a 1 there? I thought you were. Oh, okay. So that's going to be right there, isn't it? Right? That's right where we started with. We're going to go back to 1. So the limit's approaching, it's approaching a value of 1, so that's positive. What about over here? The sine of, what's the limit of 2 sin x plus 1 as x approaches 2 pi? Well, the sine's going to be 0, isn't it? So we're going to approach a value of 0 plus 1, which is positive. Right? You see that taking that limit, really, what did it really amount to? Plugging in 2 pi, right? Because we're dealing with a continuous function. So as we approach the endpoint, we're just plugging in that value anyway, right? So effectively, what we did, we just plugged in 2 pi. Yes?
So if on an AP test, the problem like this, but if you plug in 2 pi, you do wrong, but you put the limit of 2 pi, right?
Yeah. Yeah, I mean, so technically you'd want to write it this way, but when you evaluate this thing, I mean, you can show it just exactly like this, okay? Positive times positive is positive, right? And so we're going to get positive there, and so once again, we get a point of transition, and so this is going to be negative to positive is a relative minimum, okay? Yes, sir?
It's not related to this really at all. I'm like, trig identity of sin 2x equals 2 sin cosine.
Mm-hmm.
Can that be any number, or is it just 2?
No, just 2.
Just 2?
Yeah, yeah. Okay, I'm going to indulge me for a second. I'll explain why that is. It's a very good question.
It's like when I.
No, that's a good question. Those are good things to think about. So what if we did something like sine of, I'm not going to do the whole thing, but I get you the point where you can see that's the case. Sine of 3x, right? Actually, let's do 4x. I won't even have to use any other fancy trig identities. So 4x is just 2x plus 2x, right? So I could write that as the sine of 2 times 2x. So sine of 2 hand. Sine of 2 hand is 2 sine hand cosine hand, right? So that's equal to 2 sine hand cosine hand. Well, there's a sine 2x, so that's going to become 2 times 2 sine x cosine x. And then cosine 2x, take your pick. But clearly that's not going to end up looking like 4 sine x cosine x, is it? See what I'm saying? Yeah, so you can already show yourself that now it's only going to work for 2's.
So if you have any other number besides 2,
You'd have to do something like this. Right, like if you were doing something, like this is the way I would do this one, because we know what cosine 2x is. Like we could write that as the quantity cosine squared x minus sine squared x, and that's my answer, right? Okay. If you did something like sine 3x, you would just write that as sine of x plus 2x, and you'd have to use this one, right? Sine of a plus b. You guys remember that one from last year? I always have to kind of think my way through it. It's going to be sine a, oh gosh, yeah, sine a cosine b plus sine b cosine a, right? And so in this case, we just have an x and a 2x. And then you'd have to expand the 2x ones and use that double angle formula for those. But that's how I did it.
Okay, yeah.
Good question. So one last thing on this last example we looked at. We found all the relative extrema, and I'm not even going to write down what they are because the pictures tell us what they are. They tell us not only what they are, but they tell us what shape they are, smooth or jagged. What if the question additionally was, find the absolute extrema? Well, what row would we work in for that one? F, right? All we would do is we would just compare, if we wanted to find absolute extrema, we would just compare the values. Well, actually, that really wouldn't even be a very good question, would it? Because we're on an open interval. So it's really not a very good question to even ask. But, let's pretend this was a closed interval. Then we would just compare the endpoints, the value of the function at the endpoints, and at the critical numbers, and see which one of those is the biggest, essentially which one of those is the biggest, the highest of the peaks. Or maybe it could be an endpoint too, right? This is cooler to do though, finding relative extrema. This is more topical for the kinds of things we're going to do coming up. Let's do another one. Get rid of all that stuff. Okay. When are we out of here? On Mondays? How much? Oh man, that's not enough time. Okay, so I'm not even gonna start this one. What would we do before we even start doing the calculus on this stuff? Yeah, we want to be able to write the domain, right? On this last example, the domain was given to us, right? We artificially truncated the domain to just be one lap of the unit circle.